This is the second half of the work discussion that was not done on Thursday or Friday. What we've decided is if I have a physical system acted on by a force and there's some distance measurement, x, some displacement, and I want to know how much work is done by the force for a given displacement, all I need to do is to integrate the force, the f of x in this case, with respect to the displacement from the initial value of x to the ending value. We've looked at three types of things. The first one is Hooke's law, which has to do with springs. The force involved is a constant that depends on the particular spring you're looking at times the displacement. Newton's law of gravity says the force is proportional to the inverse square of the distance. That is to say, the force is a constant divided by the square of the distance. Lastly, we looked at the work done by an expanding gas. Instead of Hooke's law or Newton's law of gravity, we have that the pressure times the volume must be a constant. After doing some calculation, we figured out that the thing to do is to integrate with respect to volume from the initial volume to the ending volume, the function k over v, which is straightforward to do using methods from the first semester. In an example, you might have initially the pressure being 1,000 and the volume being 80. The volume is allowed to expand until it's 120, and we want to calculate how much work is done. Firstly, the fact that the pressure is 1,000 when the volume is 80 lets us figure out what constant K is from the law pressure times volume equals K. Consequently, the amount of work done is the integral from 80 to 120 of 80,000 over V with respect to V, which is then easily calculated. Some attention needs to be paid to the wording at times, though. A gas at pressure 500 and volume 150 is allowed to expand till the pressure is 100. How much work is done? As before, we have to use pressure times volume equals constant to figure out the value of the constant. This is straightforward. After the gas has expanded, the pressure is 100. So I didn't explicitly tell you what the volume was, but from the pressure times volume equals constant rule, the ending volume is easily found. After that, setting up the integral is straightforward as before. And then it's a simple matter to calculate the amount of work. I want to add in an extra topic here. I want to imagine that I have an object that's sitting on the surface of the Earth. Its initial distance x from the center of the Earth, I'll call r sub e for radius of Earth. We're going to move this object until it ends up being a distance b away from the center of the Earth, and I want to calculate the relationship between the ending distance b and the amount of energy that I supplied. The amount of energy, or work, is the integral of the force with respect to distance. This time I'll write Newton's law out in full. The force is a universal constant times the mass of the Earth, the big M, times the mass of this small object that we're going to move. Doing the integral is straightforward. Notice the second term is minus minus, so I think it looks better if I just write that as plus. And an interesting thing happens here. The first term does not depend on b. The first term is a constant if I'm thinking of varying the b around. The second term, though, is a constant divided by b. If you let b tend to infinity, which would correspond to you'll allow the object to move arbitrarily far away from the center of the Earth, that corresponds with giving it an energy that is at least as big as g times capital M times little m over radius of Earth. If I supply the object with that amount of energy or more, then the object will travel arbitrarily far away from the Earth. Now, I could supply the energy in a wide variety of ways. I could have a small rocket engine which would slowly lift the thing upwards at 10 miles per hour. Or I could give it all of the work, all of the energy in one big push at the beginning. We'll do that by making the kinetic energy 1/2 mass v squared equal to this amount of energy needed to move far away. If the amount of energy 1/2 mv squared is bigger than that critical value, then the old saying, what goes up must come down, is no longer true. So making the energy that I supply the energy that I need, the small m, the mass of the moving object, can be divided out, multiplied through by 2, take the square root. The speed that I'm going to need to supply to the object to make it not come back is radical 2gm over the radius of the Earth. In our previous problems, we have dodged the issue of the units by simply saying that the force was some constant over x squared. The constant ended up being derivable from the information in the problem. This time we want to do the full thing in meter kilograms second units. Newton's constant is about 6.67 times 10 to the negative 11 power. The mass of the Earth is about 5.98 times 10 to the 24 kilograms, and the radius of the Earth is about 6.4 million meters. We could figure out what the units on the G are, but as it turns out, we don't need to. I'm going to take the numbers for G, M, and R and put them into this formula that tells me this minimum speed that I need. After doing all the calculations, it turns out that this speed is about 11,164 meters per second, or 11.164 kilometers per second, if you like. If I want to convert this into more familiar units, I'll remember that 1 mile has 1,609 meters in it. Therefore, every meter is 1 over 1,609th of a mile. Likewise, there are 3,600 seconds in an hour. 1 second is 1 over 3,600th of an hour. So any place I have the word meter, I can replace it with this. And any place where I have the word second, I'll replace it with that. If I do the arithmetic, the speed that I end up with is 24,978 miles per hour. Usually, when people are talking about this, they just say about 25,000 miles per hour. This is what's called escape velocity. If you were on or near the surface of the Earth and someone gives you that amount of speed in the up direction, you will not come back. Note, you never do escape the gravity of the Earth so much as you overcome it. Originally, I was going to go on and start the center of mass stuff, but in view of all of the technical difficulties, I believe we're going to save this for our next meeting. I hope everyone's having a good day. I'll talk to you again soon.